Right. Now we are ready for the next step. So we have already seen some physical meaning down here. We're not quite ready to think about the total energy integral yet, but we are getting some physical meaning out of this. Now in the next step, now that we have talked about what happens when T decreases, let's turn this around and think about what happens when T increases. Right, so obviously if we have this expression here relating number of excited particles to temperature. So as T increases, therefore NEX increases. And we can understand that. It's because particles start from the ground state, gets excited back up to higher levels. So that's simple enough. But we have a problem. Let's look at that graph again. Not again. Let's look at that graph. Let's try and sketch that. So we have quite a bit of graph sketching down here. I'll try and draw a straight line. It's an axis. Now that I'll take horizontal as the temperature. The vertical for now is NEX. Now what would this graph look like? It is a T to the power of 3/2 graph that we are looking at. So NEX is related to T to the power of 3/2. Okay, there are some constants in front. That wouldn't change the shape of the graph. But what would such a graph look like? Now to get an idea, think about the graph y equals to x. You know what that looks like? That's a straight line. Okay, as an aside, let me try to sketch this. If I have x here and y there. Now y equals to x is a straight line like that. Now let's think about y equals to x squared. Now we know what that looks like. It's a curve, it's a parabola. So that's y equals to x squared. Why are we talking about y equals to x and y equals to x squared? Because we're interested in the power 3/2, which is in between x to the 1, the power of 1, and the power of 2. So now let's talk about y equals to x to the power of 3/2, right? The same power as that. And what would this look like? Well, since 3/2 is in between 1 and 2, the obvious thing to imagine is that this curve is in between those two. So it might look like this. So it would be a little bit less curved than x squared, but a little bit more curved than x. So that's what we are looking at. And therefore, this tells us the shape of this curve, right? The shape of the curve for this equation. So let's sketch that. Is a slight curve upwards. So that means that as t increases, NEX, number of excited particles, would go up. And this means that we have a problem. Now if you remember, N, our number of particles, is fixed. We have a fixed number of bosons, or in this example, helium atoms, that we are thinking of. So NEX, number of excited particles, cannot just keep going up forever. Surely it can't get more than the total number N. Okay, so let's say N is there. So we would expect that when the curve hits N, it has to stop. Because all particles would have been excited from the ground state. So there are no more particles left from the ground state, and you can't, the number of excited particles cannot increase anymore. So therefore, when NEX hits N, this curve has to stop, and as temperature increases further, number of particles will just stay fixed. So therefore the graph goes along the horizontal line. And that's more physically reasonable. Okay. And now we are ready to finally answer the question, not about the total energy yet. We are finally able to go back to mu. Alright, remember I raised the question just now as to whether mu can actually ever hit 0. Maybe not in the exact words, but let's take a look at that now. Alright, we know that mu keeps going towards 0 as temperature falls. Right, as temperature falls. Does mu actually reach 0? So let's go to higher temperature. As temperature falls, okay, mu decreases. Okay, let me just cross that out. Let's think about what happens when the temperature reaches this point, where the two lines meet. Now, the N here, if you recall, was determined by another integral that was given by that. Right, we had the integral there for N, which contains the chemical potential there. Okay, and we have understood from all the graph sketching that as temperature falls, mu has to increase towards 0. Okay, now let's look at this graph. As temperature falls, we will be moving along this line. Now, and when we reach this point, we switch to this curve. And this curve was obtained from here, from this expression for this integral for N. And you remember how we got this? We got this by setting the mu to 0. That's why there's no more mu there. And that means that on this curve, on this curve, mu has been set to 0. So this means that when from higher temperature, when we reach this point, mu becomes 0 at that point. Okay, so if we imagine actually plotting a graph of mu, if we like, then at this temperature, okay, we would expect that at higher temperature, mu has a negative value, and as temperature falls, mu increases towards 0, and when temperature reaches that point, mu goes to 0. And thereafter, mu stays at 0 as we come down this curve for the excited particles. So now we have a much better idea about how mu changes. So the next thing we want to look at here is this temperature. There is something interesting about this temperature. There is something interesting about this temperature. Now, this is the temperature below which particles starts going into the ground state. Now, we associate the idea of going into ground states with the idea of condensation. Okay, like steam condensing into water. So this is the temperature at which particles starts condensing into the ground state, if we start using this description. And because of this analogy, this temperature is given the name of a condensation temperature. Condensation temperature, and is denoted by the symbol T with the subscript Be. Be for Bose Einstein. So we call that TBE. Right? Temperature where below which particle starts going into the ground state at a massive, a macroscopic scale. And this this phenomenon in which lots of particles starts going into the ground state has a name. It's called the Bose Einstein condensation. Okay, now just while we're here, let's learn another term. The particles that would have gone to the ground states, alright, all these particles at the ground states, they have a name. They are called the Bose Einstein condensates. Right, just as when steam condenses into water, we say that water is the condensate of steam. So here we call the particles in the ground state the Bose Einstein condensate. Now, the next point I want to do is to look at to see how we might find a formula for this condensation temperature. Now, if you look back at remember that we already have a formula for NEX, for the number of excited particles. We had this formula here that relates NEX to T, and the T we are interested in is the TBE, which happens when NEX is equal to N, right? So therefore all we need is to set NEX to N, and we can solve for the condensation temperature. Right, so let me make that clear. If I set NEX to N, then the T there would be TBE. Okay, so we make the substitution and then we solve for TBE. Let me just write down the answer. And this is what the solution for TBE looks like. H squared over 2 pi m KB bracket N over 2.612 volume, power of 2/3. That's the TBE. Okay. So with this TBE, we can actually calculate an answer for the TBE of liquid helium if we assume that it's a boson gas. Right, you can see how big an assumption that is, because we are talking about liquid helium and yet we are going to assume that it is a gas. But let's press on with this assumption. In the case of liquid helium, now we know these numbers. That would be the mass of the helium-4 atom, and we can actually Google for the volume of 1 mole of liquid helium-4 is about 30 cm cubed. Right, when N here is the Avogadro constant, M there is 4 times of the atomic mass unit. So using these numbers, we can now calculate. Right, before that, I think this might not be a H bar. This might just be H. Okay, we have to check that. So let's take that as H squared for now. Right, before these numbers that we know, we can then calculate an answer, and you find that it is it's about 3.1 Kelvin. So this is for liquid helium-4. So we have a number there. Now we'll come back to this number. Okay, now we are finally ready to calculate the total energy. So let's look at the total energy expression again that we wrote down just now. Now the total energy expression is given here from this formula. We have written down the density of states expression and the Bose Einstein distribution. And remember that we were not able to integrate this because we did not know what mu was. Now we know, well, not completely, but we know that mu is 0 below the Bose Einstein. Let me say that again. We know that mu is 0 below the condensation temperature. Now we don't know how mu changes at higher temperature above TBE, but let's worry about that later on. For now, at least for the range of temperature between 0 and condensation temperature, we know that mu is 0. So therefore we can finally try and integrate this to find U within that range of temperature. Okay, so let me try and write that down. Now what we need to do is to write down the expression for U with mu equal to 0. Okay, let's see what we have. 0 to infinity. Now we have energy. Remember, we have 4 pi m v over h cubed square root of 2m e. So this is the density of states, and we have the Bose Einstein distribution, which is e to the power of energy over kBT without the mu anymore, minus 1 dE. Okay, so this is what we have, and what we've done is we've set mu to 0. Alright, because this is true for temperature between from 0 to TBE. So that's the condition that we are working in. So how can we integrate this? Well, let's look at where the variables are. So the variable is E. That's the integrating variable, and we can find E there. We have a e to the power of half there, and we have an E there. So E times e to the power of half is e to the power of 3 halves. Okay, and there is a formula from the table of integrals that we can use. Let me write it down here. X to the power of 3 halves over e to the power of x minus 1 dx equals to 1.783. And that means I have made a mistake just now. Now let me go back to my previous writing on about n, on integrating n. So let's compare the two formulas. Now I have just written down this formula from the table of integral when I have an x of 3/2 in the integrand. Now, and these two numbers are the same, right? That's probably not correct because I have a x to the power of half there. And indeed, it is not. Alright, I'm looking at the right place in my notes now. That should have been 2.315. Right, that's the correct answer for the last integral. Okay, but this result of that integration was correct. Okay, coming back now to u. So let's quickly see why this can be used for this integration. We have e to the power of x here, and we have e to the power of this argument there that contains the e. So all we need is to make the change of variable by setting this argument to x. And in the denominator we have e times e to the power of half. So that's e to the power of 3/2. And here in the formula we have x to the power of 3/2. Okay, so this connection means that we can actually, by making the right change in variables, we can then make use of this formula and carry out this integration. So I'm just going to write out the answer directly. It's 0.7704 kb and then t to the power of 5/2 over. Now in terms of TBE to the power of 2/3. Now should just remind ourselves what TBE looks like. Right, we got TBE just now, and it looked like that. So there's this whole chunk of terms down there. So this whole chunk of terms would come in there. So in other words, if you write down everything, this looks really complicated. But for our purpose, we are mainly at the moment we are just interested in how U changes with temperature, because we want to use this to obtain the heat capacity. Now, heat capacity is du dt, so with this formula we can already differentiate t to the 5/2, and that gives us t to the 3/2 with a bunch of constants before it. And now we are ready to try and sketch a graph again. Okay, this time I want to sketch the graph that we talked about at the start when I first mentioned London's explanation for the superfluid. I talked about how London make use of the heat capacity graph of a gas of boson. Alright, and I actually sketched it. Right, I think I have it here. That's what I sketched just in the previous video. So I said that London made use of this result for the heat capacity of a gas of boson. The fact that the shape and the peak temperature is similar to those of the measured heat capacity suggested to London that this might be a possible explanation for superfluid helium. So now we want to see how this result came about. If you look at this expression that I just obtained, we've just obtained that C, the heat capacity, to be careful here, the heat capacity below the Bose Einstein, the condensation temperature, is given by a constant times T to the power of 3/2. Now we already know how to plot the graph of T to the power of 3/2. It's a slight curve in between a parabola and a straight line. And when you plot that, that's what this is. This curve here that London used. So this curve is the T to the power of 3/2 curve. And the curve is plotted all the way until this value at 3.1. Now, that number looks familiar. If you remember the calculation or the result I've written down for the condensation temperature earlier on, I've written down 3.1 Kelvin. And in fact, that's what this is. In this graph, alright, the peak is given as 3.1 Kelvin. Okay. Now above that temperature, there's a sudden change, there's a sharp change in the graph for the heat capacity. Now there's a physical reason for this. Alright, there's a simple physical reason for why it suddenly changes or decreases. It's because by the time, if you remember how the condensation temperature was described, it was described as a temperature below which particles start condensing into ground states. But if you think about increasing the temperature, then when temperature increases above the condensation temperature, all the particles would have come out of the ground states and become excited. Alright? So there's no longer this reserve of particles in the ground state that keeps coming out as you warm it up along this curve. Alright, so beyond this temperature, there's a sudden change in the behavior of the system. Instead of particles coming out from this reservoir, this ground state collection of all the bosons, suddenly they're all excited. Okay, and after that you have these excited atoms which will continue to gain energy if you keep raising the temperature, but the behavior is now different. So we will not be looking at how to derive any formula for this curve. Right? The formula for this curve has been derived by Einstein some years before London proposed his superfluid theory. So we're just going to assume that it is some curve coming down from the peak. Now, but what we can understand is this limit at the high temperature. Now at high temperature, this curve approaches a straight line. Alright, and but if you're thinking of 1 mole of liquid helium, then the heat capacity goes to 3/2 R at high temperature. And 3/2 R is in fact the ideal gas heat capacity, if you remember. And the reason is quite simple. At very high temperature, the particles become has a lot more energy, and the average energy will be a lot higher than the spacings between energy levels. So it becomes, so we have this situation where the particles are spread among the energy levels, and that the number of for any energy interval, you have a lot more energy states than you have particles. And that's the picture we have seen for the ideal gas. So that's what this turns into at very high temperature. So now we have understood, apart from not having derived any formula for this part of the curve, just above the condensation temperature, we have in essence understood all the rest of this graph. Okay, we'll stop here now.